Good morning, everyone. We resume our discussion that we started last lecture about symmetric systems, spherically symmetric systems. So, as I said, we changed strategy, and what we are doing now is to not simplify the equations by making them linear, but by simplifying the system. Meaning we are not dealing anymore with a general object, but we are dealing with objects that can be dealt with a spherically symmetric, that are compatible with a spherical symmetric object. So they obey this sort of symmetries. I showed you that for convenience, it's good to use the Minkowski, to use the, let me make it bigger, to use spherical symmetric coordinates, as one would do in a three-dimensional space. But now one has to take care that we are dealing with a curved space-time, and therefore when measuring the circumferences and surfaces of spheres, so the circumference of a circle or the surface of a sphere, we need to take care that the radius, the meaning of a radial distance with respect to the center of the sphere, where r now is the diameter of the sphere, is different. Okay? So there are two different radiuses. One that refers to the measure of surfaces and length along the surface, and one which is referring to radial separations with respect to the center, defining the size of your sphere. So we need to take care of that. We then wanted to identify a metric that was compatible with this sort of spherical symmetric scenario. And we started with a generical way of writing down one of our four elements. We wrote down all possible elements that are referring to the alpha beta parameter, ranging from 0 to 3. We used for the angular dependency the same that we use for spherical symmetric system in 3D. And then, because of the symmetry that we are implemented in our system, many of the terms dropped as we discussed, okay? So that in the end, we are left with that. Finally, we imposed, we identified a new, you see, it is this mixed component between time and space, a new symmetry that we have to impose, a new symmetry, an additional symmetry that we have to impose, because if the G0R term would be different than 0, we would have a privileged direction in the theta and phi space. And this would break the symmetry, the spherical symmetry, because it's a vector identifying a privileged direction. Okay? We don't want that. Any possible direction in all possible coordinates that we are using must be spherical symmetric. So also that one must be equal to 0. What we were left with in the end, what is a simpler expression. You see how things simplifies when you impose symmetries to your system, in which then we re-expressed the G00 and GR term through this exponential function for convenience. And then if one would also make a full derivation, we'll find that. And moreover, we imposed as well a static metric. And in fact, this is reflected by these coefficients. You see that we have a radial dependence only. There is not a t dependence, because otherwise we would have an evolving system. Then, because of Birkhoff theorem, one can show that this metric is actually valid also for still spherically symmetric systems, but with a time evolution. And the only time evolution that is allowed in a spherically symmetric system is an isotropic expansion. Right? It's a sphere that gets larger or smaller. Okay? This also already proves you something that we have seen in the previous lecture when dealing with gravitational waves, meaning that in a spherically symmetric system cannot produce gravitational waves, because the metric looks like that. And there is not something of the sort of the perturbation that we have seen in the previous lecture when dealing with gravitational waves. Okay? So Birkhoff theorem tells you this metric is valid also for spheres that are expanding or compressing, therefore or pulsating, as stars do, for example, but as well tells you this is the metric, there cannot be the perturbations that we have seen when we dealt with the gravitational waves, and therefore there is no gravitational wave production. You can already get that from this theorem and this metric. Then we proceeded, and what we wanted to do now is to identify the G00 and the GRR term, or if you wish, the functions AR and ER and BR that fully characterize the two coefficients of the metric. To do that, we do what you already know, meaning we need to apply and solve the Einstein fields equations such that the metric that is hidden both in the energy momentum tensor actually and in the Einstein tensor, this needs to be solved such that given a source, which might be matter, which may be a field or whatever, gives you a certain metric. Okay, so this equation allows you to do that. So what we did then is to compute the Christoffel symbols, to compute the Ricci tensor, to compute the Ricci scalar, such that we have the full expression of the Einstein tensor, which we expressed in this way. Okay, so there are steps in which involves this sort of computations, the Christoffel symbols and so on, and you arrive at this expression that we have seen in the past lecture. Then the other piece of information that is missing is the energy momentum tensor. And here you see we need to specify which kind of material, which kind of objects we are dealing with. And for a simple case, I just consider this energy momentum tensor, which is useful for matter only. There is not a gravitational, an electromagnetic field, for instance, which would produce a different metric, as we are going to see in the next lectures. So I just consider matter, and if you wish, if you are considering as well a pressureless component, dust, in which the pressure is equal to 0, you would be left only with rho, u mu, u nu, dust, as we have seen also in the previous lectures. In this case, I'm considering all of it, so pressure is going to be different than 0. Doing that, we derived already in the past lectures these expressions, so these are the explicit form of the components of the energy momentum tensor for an ideal gas, expressed by this equation here. Okay. Last time I made a mistake because I mistook this C, and I fixed it. Okay. So in the lectures on the web, you find as well the fixed. The results is the same. Okay. It was just misplaced in this part here, in this very step. Okay. But the rest is exactly identical of what we've seen last time. Good. So this is where we were standing last time. We have the energy momentum tensor, and we have the Einstein tensor. Therefore, what we can do is to proceed and evaluate our explicit terms of the metric, as we are going to do now. Good, let's get started then. Let's give a look at the GRR. Equal to what? Let's find out. So what we are going to use is the G00 component of our Einstein fields equation. And what we do, we just plug in the expressions that we got from the previous steps. So we just do that. We have 1 over r, exponential of 2a of r, d over dt, r multiplied by 1, g rr minus 1. So this would be the e to the power of b. Okay, I re-express it back in terms of the metric because I'm just giving you the expression for GRR directly. Okay. Equal to energy momentum tensor, APG, c to the power of 4, rho, c squared, e to the power of t, e of r. Then we have c power of 2, c to the power of 4, that they cancel out. Then what we can do is to bring this, that's an r squared, by the way, r squared, This R square, we can bring it on the other side. And then what we do, we isolate this term, okay? And we just integrate. As well, the 2a and the 2a goes away, right? They're on the two sides and they're both positive. So what we do now, we just perform the integral such that we obtain our R1 minus G R to the minus 1 is equal to 8 pi G C to the power of 2. And then we have the integral. We have the integral of what is left, which is rho R square in the R. R square prime, the R prime. Okay? So what do you see already here? That the G metric depends on the distribution of the matter density. Okay? It means that to know the explicit form of GRR, we need to know rho, the distribution of rho. Okay? Nevertheless, we can play a trick. You see that we have a 4 pi here, an 8 pi here, that we can write as a 2 times 4 pi. But look, what's that? 4 pi rho R to the power of square dr. That's the matter content within the radius R. If we integrate between 0 and a certain radius R. Okay? Therefore, we can define, you see this is the density times a volume, which is a matter content. Therefore, we can define MR as 4 pi integral of rho R prime square the R prime. This is the source. Now what we do, we just isolate our GRR with respect to this expression where we can use this definition. With definition, actually, we are expressing the integral as the matter content within the radius R. So what we get is GRR equal to 1 minus 2 GM over C square R. That's RR, so minus 1. Then we can do something. You see we have this guy as the unit of a length. Therefore, we can define what is called the Schwarzschild radius, Rs, which is equal to 2gm over c squared. We shall continue and go for the other coefficient of the metric, G00. Equal to what? Again, what we do, we just use Einstein fields equations. This time for the RR components, 8 pi G over C to the power of 4 TRR, exactly as before. Then we plug in the expression that we found in the previous steps, meaning the explicit version, explicit Einstein tensor and the Einstein and the energy momentum tensor. And they were 1 over R2, GRR, 1 minus G, RR, to the minus 1, yes, plus 2 over R, dA over dr equal to 8 pi G over C to the power of 4 P GRR. Now, what we can do, you see that we have this term that can be re-expressed as a function of MR. you see that MR is equal to that. So here, all of that contains a 2G MR over C squared. Therefore, we have MR plus, multiplied by those factors times this guy here. Okay, so you see that that expression that I marked there, between parentheses, is exactly this guy that can be expressed with respect as a function of MR. So we do that, we plug in our definition of MR here, and we isolate this term, because we are looking for the G00 term that is expressed in terms of A. Remember that G00 was defined as E to the A of R minus, because it's a time interval, time-like interval. Okay, so we are aiming at this function here. So we have GRR. Oh, sorry, it doesn't cancel out, this remains. So we just isolate this guy here, and we get 2 over R dA over dR equal to 1 over R squared GRR M of R, that is popping up by the substitution of this term given this definition, the definition of MR, 2G over C squared R plus 8 pi G over C to the power of 4 P GRR. Fantastic. Then we have 2, 4. Then we have R, and R. Yes, because I'm multiplying everything times R. There is nothing canceling, and it appears there. Good. Now you see we have the expression that is characterized with respect to dA, dR. Okay? There is GRR that appears twice. So what we do, we just put it together. We just group it. Therefore, we have dA over dR, which is equal to G over C squared, GRR, MR over R to the power of 2, plus 4 pi P R. And now, everything is clear. There is this GRR, but we know what GRR is. So we just plug in our explicit expression that once more depends on the matter content. Okay? Remember that this is a function of R, MR as well. Yeah, actually, it's better to do like this. Right, I was too fast here. So this is a function of R. The Schwarzschild radius is a constant given a certain source. So I will introduce it later. Okay, so bar this thing. This was a mistake. Okay, let's continue. So we have GRR. We plug it back in here. And what we get is G over C squared. Then we have MR plus 4 pi P R squared over R minus 2G M of R over C squared. Now we have an equation that expresses A, that you can solve. How? You cannot get an explicit expression now, because we don't know what is the matter distribution of our object. Okay? But you see that once this is expressed, once this is found, you have A, and therefore you have your metric. G 0, 0 is equal to minus E to the A of R. We have our metric. What about the other? Should we continue blindly and just look for the other Einstein fields equations and solve and find the other components of the metric? No, because we already imposed the symmetries. And actually, everything is explicit with respect to that. Because we have that G theta theta that you can read from the previous boards in which we expressed the metric is just equal to R. And G phi phi is equal to R sinus of theta. This is coming from the symmetries. As well as the all other components of G mu nu are equal to 0. Again, this was from the symmetries. Yes? Sorry?
Is there a reason why we dropped the 2 of the A? So is it just a typo or is there a reason for something in the exponent or metric? I think usually we initially define it as 2A.
Yes, you're right, 2A, sorry.
And the book we did it also, so it's just, it might be.
Yeah. No, it's not intentional. I just forgot about it. Yeah. And the 2 was, you could absorb the 2 in A, so it doesn't matter. But it's just done, thanks for pointing this out, for convenience, because this enters, this expression enters in the 4 interval where you have all squared expressions. Okay? If there would have not been this at the beginning of our expression, here we would have all square roots of the function. We would have to restore divide by 2A every time. So this is more annoying than just canceling out the 2. Okay. Good. We have our metric. But now we don't know what to do with it, because we don't know what is M. So we need to search what M is. Let's use the space that we continue here. Good. And now what? M of R is equal to what? How do we find it? Let's see. Let's see. We need to consider a specific object. We cannot, be completely generic. So for interest, because most of these equations are applied to astrophysical objects, let's take a star, for example, or something that is a very simplified version of a star. A star is what? Is a sphere, therefore we can, or roughly a sphere, that we can, for which we can apply this symmetry, spherically symmetric metric, and is a self-gravitating object. What does it mean? It means that the distribution of the matter as a function of radius of these objects is given by gravity alone, plus the properties of the objects. So we have the players are gravity and the pressure of the material composing our object. Okay? So if you remember, I remind you that in the energy momentum tensor, the pressure is a key object. And the pressure depends on how this object is structured and composed. A white dwarf, if we take a white dwarf, have a relationship between the pressure and the density which is different with respect to the one of the sun, for instance. Okay? Good. So it's a self-gravitating object, and if you want, it's a ball of gas. better to say plasma. Okay? But let's ignore the plasma thing, and just let's think that on scale this is neutral. Okay? Just neutral object, and is a ball of gas. Okay? So that I can ignore charges, magnetic fields, and all of that. Otherwise, we should consider their energy momentum tensor components and things get messy. So it's a very simple star. It's a very simplified star. Jupiter might be a better representation of this. Okay? So again, a gaseous object which is self-gravitating. So it obeys better this description. Then what we do? We need to solve all equations simultaneously. So as I said, we have gravity, so rho, and as well as the density. These are the components of the energy momentum tensor, if you wish, okay? So we have gravity, but we have everything because we have G, 0, 0, we have G, R, R, we have G, theta, theta, and we have G, phi, phi. And we already know these expressions. These are given. They are a function of P and rho. So this is done. The business is done. What we are left is with the hydrodynamical part. Hydrodynamics. And therefore, we need to solve the hydrodynamical equations that you already know. Implicitly, I gave them to you already. The nu, T nu equal to 0. These are the equations of hydrodynamics. Because the zero component, you see that we have a repeated index, and then we have mu. Mu equal to 0 gives you the energy conservation. Then the components mu equal to E, so 1, 2, and 3, gives you the Euler equation that expresses momentum conservation. Then what we do, that's not enough because we need to constrain better our system because the variables are more than 4, because here we have 4 equations. We have 4 times mu, so we have 0, 1, 2, and 3, 4 equations. Because the variables are what? Rho, the density, the pressure. Then we have the velocity of each volumes of our material, V, and these are 3 variables because we have V1, V2, and V3. And then we have also the energy that is associated to each the thermal energy which is associated to each little volume of the portion of our object, okay? So you see that we have 6 equations, 6 variables. There we have 4 to constrain those. So what do we need to add? We need other equations, we need other constraints, one of which is matter conservation. The nu G, the nu J nu equal to 0. Okay? Where J nu is the matter current. Now I don't want to go into these details because then we would be too much deviations into the hydrodynamics. But I give you the concepts and this equation, where J nu is the matter current. Expresses matter conservation. So we have 1 additional equation. We are at 5. We are short of 1 equation. So what we need to impose, we need to understand what are the intrinsic properties of our system, and we need to introduce an equation of state. That relates pressure to density and the thermodynamical properties of our system, such as, for example, is the temperature. What's that stuff? You already know PV is equal to nRT, for example. Okay? This is for an ideal gas. Okay? If you have other sort of gases, then you need an equation of state that is good for this sort of objects. Many times, if you are assuming, if you're assuming, for example, your object to be in equilibrium, it's in thermal equilibrium, then this is a constant and you drop it. Therefore, you have a direct relationship between the pressure and the density, P rho. 6 equations, 6 variables, the system is closed. For hydrodynamics. 4 equations, 4 variables, the system is closed for gravity. You can self-consistently build up your model for your star, Jupiter, or whatever. Good. I just give you an expression for the equation of state which is often used in astrophysics, which is the so-called polytropic equation of state. In which the pressure is equal to the pressure to a certain location times rho, so the density at that location where we estimated the pressure, divided rho to the power of gamma. So it's parametric, and the parameter gamma, which is called polytropic index, polytropic equation of states, polytropic index, characterizes the material of your object. And this expression is valid for adiabatic scenarios. Okay? If you are dealing with an adiabatic expansion of compression, this polytropic equation of state is valid. And I give you just a couple of numbers. If you are taking a white dwarf, then the polytropic equation of state is equal to 5/3. If we are taking some other star, okay, always in a quite simplified manner, gamma is equal to 4/3. Now, last thing we would like to do is to have some better intuitive understanding of the distance with respect to the center of the radius, okay? Because as we see, we characterize two different radiuses, one to measure the surfaces and length over the surface of a sphere. The other one was to define the radius of your sphere. So let's try to understand what is, to get an intuitive understanding also of length in general in this sort of metric. So what we would like to do is to link our metric and try to map it to a Euclidean space. So what we do, first of all, we make our life simple, and for simplicity, we set theta equal to pi half, and at the equator. So we are basically looking at the equator, okay? This is no lack of generality, because we can always rotate our system such that the point we are considering end up to be at the equator. Okay, so no lack of generality. And then we take a time slice. The length, so I'm taking only part of the contribution to the length of our, so since t is equal to 0, the t is going to be equal to 0. Therefore, we have 1, so the time component drops, and our 4 elements in the end is just a length in our three-dimensional space given this time slice, minus let me call it R bar over R. So I'm calling R bar the parameter 2gm over c squared, okay? That, again, within this context, is still linked to a matter density distribution, but let's call it like this. So the R square plus R square, the omega square. Then let's look at the three-dimensional case. Sorry, in a three-dimensional Euclidean space. 3D Euclidean space. And what we have is the R square equal to the Z square plus the R square plus R square the phi squared. 3D polar coordinates. That's the phi, it's the survivor. That's the theta, yes. Now we can rewrite this, the z, in terms of a derivative with respect to the radius, such that we have the z over the r squared. Here we need the z, therefore I multiply times the r squared, plus the r squared, and again we have r squared, the theta squared. And then you see that we have the r, I just group it together, and in the r we end up with 1 plus z prime, where z prime is this guy here, squared, the r squared plus r squared, the theta squared. Now what we are doing is going to map this the three-dimensional slice of a four-dimensional space of a Minkowski time with our metric above. Sorry, the three-dimensional space with the four-dimensional one, which is our time slice. So let's do that, and what we care about is only at the first coefficient, the R. You see, I'm focusing on this guy here. And we impose that the corresponding element of the metric in the Euclidean space, in the Minkowski space is equal to that. So we have 1 minus R bar over R equal to that. 1 plus Z prime squared. And then we just isolate Z prime. Okay, so we have Z prime squared. We are going to have our expression, so I'm just isolating this term. We do the square root, and then we integrate. Okay, so we just solve this equation for z. Let's go straight away for the integral. So our z prime, which is going to be equal to plus minus square root of s r bar, r minus 2 r bar. Yes?
So did we already integrate m out or not?
Yeah. Then there is the integral. So you isolate r prime, and then you perform the integral, you end up with that.
I mean, since finding r bar, did we already integrate m?
No, yeah. Here we are performing the, yeah, you are right. So the trick I'm applying here is that I'm considering myself like this is our object, and I'm restricting myself to the scenario in which the matter ends up here. So yes, so it's already integrated, because then when we are at radius is larger than the size of our object, m is constant. Yeah, no, that's correct. Okay? And in fact, if I perform this integral, as is stating right, m was considered to be constant, because I'm outside the object. Good. And this is our z. Look, we have a relationship between the z coordinate and the radiuses. So it looks like that when we move along z, now I'm taking again a slice of this space, the radius is changing. Okay? So when we make this time slicing, you can see that r is changing, and the change as you move along the z direction is such that you can consider r pi squared, r pi and r pi and pi r squared, the circumference and the surface of a sphere. So you see it's changing itself such that that guy for a fixed r, meaning the radius of the source, or the radius the radius of that characterizes you and your location between the center and yourself is fixed. Okay? So, little summary. In the past lecture, as I repeated today as well, we end up with identifying the energy momentum tensor T for an ideal gas, an ideal fluid, sorry, not gas, fluid, because it's more generous in fluid, and the energy momentum and the Einstein equation G. Once we have that, we can solve the equation. We did it for the component 0, 0 of this expression, and we end up identifying the RR component of the metric, fixed. Then we moved on. We did the same for the RR component of our set of equations. And we identified an expression that is locking up A, which gives you function A that gives you the expression for the G00 component of your metric, locked, with the caveat that this function depends on the matter distribution of your source. Okay? Therefore, what you need to do if you want to be self-consistent, you need to solve as well the properties of your source. To give you a fully general relativistic approach for this sort of scenario, I consider a simple star, which is just a ball of plasma, okay? A ball of sphere, no magnetic field, no anything of these sorts, okay? Just a self-gravitating system in which the pressure, rho, and gravity are playing together, and are playing together following the rules of gravity and of hydrodynamics, in which we have these conservation laws that are the ones of hydrodynamics, in which we have energy conservation for the zero component of this set of equations, and the Euler equation that represents momentum conservations. Then we have seen that we have more variables than just the equations that we have there. We have 8 equations there. 4 are to lock down, to constrain density. We are left with 4 equations, but in hydrodynamics we have 6 variables, 6 free variables, which are these ones. Therefore, we need to introduce 2 new equations. One is matter conservation. That's just telling us that there is no annihilation, for example, going on in the system, or there is no creation of particles in our systems. And an equation of state that is linking the pressure to density. Given a certain density, we have a certain pressure. That's what the equation of state is telling us. And for that, we need to specify which kind of material, which sort of configuration you are dealing with. So here I gave you, just to remind, your Physics 1 lectures in which you have your ideal gas. And an equation of state that is very often used in astrophysics, which is the polytropic equation of state, in which you are free to choose your gamma, your polytropic index, to characterize the specific material and scenario that you are working with. And you see that different objects have different equation of state, so that's the message of this. Then perhaps I anticipated too much this expression, would have been better to do it later on. But what I did, I placed myself outside the object, and now the MR is a constant, okay? Because there is a zero contribution. If I'm integrating over larger radius, the matter that we have is inside here, so it is not going to change anymore. And therefore, this is going to be a constant. What was depending on the distance is now a constant. And if I now look at the, I'm trying to link our slice, time slice that represents this length in the rest of the spatial coordinates to a three-dimensional Euclidean space. I imposed this guy equal to that, just to investigate what is the dependency of Z with respect to the radius as meant in this metric. And we did the trick, we isolated Z, we perform our integral, and we got this expression. Okay? If we now make a plot Z with respect to the radius, so our interpretation of the radius defining the distances, you can see that as we move along Z is changing size. What is this telling you? That it is mapping on a three-dimensional space, the radius of your spheres, so the surface of your spheres is scaling not as a constant, but it depends on your Z position. Okay? This is a sign of the curvature of the space-time, of the Minkowski, of the metric that we are considering above. Good. Now we can have a break. We can resume at 10:15, and we will continue with the Schwarzschild space-time, and we will start to speak about black holes.